Okay, folks, last day of space time. So I'm gonna give you one more homework. It'll be due next Friday. Put it in my box. Be here. It will just be on like adiabatic shit and like gases and blah blah blah.
No, are we allowed to ask questions for that?
I hope to do. Ask them sooner rather than later. If you need to, I'm happy to hop on a Zoom, do a group Zoom. You guys are doing like homework hour. You're like, how the fuck do we start? But one thing that I've noticed that's pretty consistent about the homework so far is that you are doing really well and then just using the wrong equation. And so majority of the feedback is, just like look at this slide specifically. I wrote it right here. Right? It's not even derivations. So sometimes rather than sort of spinning your wheel and trying to like, how do you even get started here? The better thing to do is go back to the reference material and reread it. Because almost exclusively everyone used for the space person who's dropped versus space person in orbit. Almost everyone used the space person who's dropped. They did it perfectly, and then just forgot that there was a completely different equation for person in orbit. And it turns out you have to use that over and over and over and over and over and over again. So they're lost. Right? If you use the two, they're almost exactly the same. One has a factor 2 in front, one has a factor 3. That's it. Right? So your answers aren't horrible. You did the right thing. You're just using the wrong equation, right? So generally speaking, I think, there's definitely lessons that I learned, specifically about how best to teach a class. So if you are taking a class with me next semester, I don't know if anyone is. You are? What are you taking? Okay, so computational will be flipped already. So you'll enjoy that. The book. And the cookbook is very specific. So we'll try and stay on track as close as possible. And that's really important. And I think one of the things I learned about this class, kind of winging it, you can get lost. And especially with thinking about what our goals are or what we want to get through, then it's a little tricky. And stay on track. I wanted to give you 8 homeworks. We will give you 6. But that's on me. In some respects. It's on you in some respects too. But it's also on the professor that gave you class of football in some respects. A group effort. Okay. So today we'll just finish with, now it doesn't say it's here, but we're gonna finish up our discussion of Jupiter first. Then we'll talk about the other giant planets. And then that's it. Actually, clouds and vertical structure we already done. Question before we get started? Derek, you have homework. It'll come out either today or tomorrow, depending on how lazy I get. And it'll be due next Friday. And I'll be available by Zoom or by nothing. Okay. So, how to build a magnetic field at home? You're God and you're bored. No, you're like God's younger cousin, and you're bored and you don't know how to do all the things that God knows how to do, but you have heard him talk about it, and he's like, "Oh yeah, can you build me a magnetic field?" You're like, "Oh, for sure. I got all these plants lying around. What do I need to make them?" So the recipe for a magnetic field. I spell that right. That's egg rotation. Is that it? Flux is what you'll get. Like you can get flux.
Yeah.
Yeah, you'll get it.
Oh,
But you might need something else. Differential rotation. What does that mean? Right. So you need shear. Conductive, yeah, so what does conductive mean? Conductive to what? Some would say that like the table is conductive to heat, right? Like, what am I conductive? Yeah, I mean, you're thinking of the right thing. Good. Okay, that's true. It's more complicated, obviously. Um, you needed a differentially rotating. Good, we did that. Liquid metallic, good. Hydrogen. Now, hydrogen doesn't really matter, can be whatever, but it needs to be metallic. Okay. That creates a dynamo. So a dynamo is the result of moving electric charges, ions and electrons. And the motion of those electrons creates magnetic fields. So if you're taking E and M, then I'm taking E and M. Which E and M are you? Two. Okay, so you should definitely know this, right? So how do you generate the DVT? Oh shit, I didn't think I'd have to remember something from another class. All right, when you get that, let me know. Okay,
That's equal to the curl of the electric field.
curl of the electric field and
That's negative.
okay. So what does this mean? Means if you have a bunch of electrons, remember that the electric fields are things set up by things with charge. And if they're twisty, then I generate magnetic field. That's the dynamo equation, more or less. Right? So you have a time varying magnetic field, and it's generated by the motion of electrons or ions. Right? So if the electric field doesn't curl, you don't get it. Jupiter has such a big magnetic field that it's been known for a long time to accelerate particles. And as it does things, right, so for example, there are particles that head down its magnetic field lines, and since they're decelerating, they have to get rid of that energy. And they do that by something called cyclotron emission. And that happens in the radio. So if you have a radio telescope, and it turns out you can build a radio telescope as an undergraduate, that I've always wanted to do for Astro 4000. You basically take rods and place them at specific locations, spaced out. Phase them so that you get the electrical conduction from each of them, wire them all together, and then you just see how the voltage changes. And as they absorb radio waves, you will get enhancements in the voltage, which you can absorb as information from there. Now, if you tune them improperly, you'll pick up nearby radio stations. And that's not what you want to do. So you have to design them so that you grab this cyclotron emission. And what's amazing is that the size of Jupiter in the sky, when you observe it in the radio, is as big or bigger than the moon. The Jupiter's magnetic field is so large that even from our distance, it's a giant blob as it goes across the sky. And you can watch that in these images. Okay. 10 million kilometers. Boom! Mega, mega. We see aurorae. So we see aurorae at almost all the planets, different types. They're not always associated with magnetic fields. In fact, at Mars, we find that there are aurora, but it happens because there is not a magnetic field. So aurora is just when particles from the sun smash into the top of the atmosphere. That's the only thing you need. We are familiar with the fact that they travel down magnetic field lines because we have a magnetic field. That's how we see it. And so the similarities between us and Jupiter are that, right? They both have strong magnetic fields. They both take particles from the sun, channel them, smash them into the top of it. Okay. That's what it's like. Yeah, so this is in the ultraviolet, I believe. Hubble Space Telescope. What you're looking at here is the particles smashing into the top of the atmosphere. As they do that, they have a lot of light, and so they bright that light back to us. What are you looking at?
Like the top of Jupiter.
Yeah, top of Jupiter. That's where the magnetic field is coming out. So if you've ever been curious how this happens, probably shouldn't go on the side track right now, but I'm doing it. It's fine. Okay. All right. You have differential rotation in here. Right? So the rotation happens like this. And then this is slower up here. And what that does is it wraps magnetic field like this. Okay? And it shoots it out the top. And since magnetic field lines can't end, you have to go back in. That's deeply oversimplified. That's how it is. It looks like a box. And that's, yeah. Okay, so this is where it's coming out. You can see these lines. What's that? That's Io footprint. So this is the material from Io's volcano. It gets electrically charged. Once it's charged, it follows magnetic field lines. It travels up the magnetic field line and impacts the northern pole of Jupiter. What's that? That. Nope.
The other moons.
Yeah, these are the other footprints. So there's two more moons here. So material is electrically connected from the surface of Europa and Ganymede. And that material is ice. Let's say a little water comes off. Let's say your water gets associated by light. Suddenly your water is OH plus, or you have H2O minus. Now that thing travels along the magnetic field line and smashes top. Right. Classic. Okay. Saturn, big, kind of comparable size to Jupiter, a little bit smaller. When you add in the rings, it's bigger, obviously. The density, floating water or no? Floating water. So if you can find a big enough pool, you can float Saturn in. Moment of inertia. More or less differentiated than Jupiter? Remember? More. Crazy. Now, what was the mind-boggling thing I told you at the end of last class? Still differentiating. Because it's still differentiating, it's twice as bright as the light that it gets from the sun. Okay, so if this is more differentiated, what do you expect about its interior? Yeah, right. So counterintuitively, the more differentiated it is, if they were born at the same time, it's likely to be producing less heat. Right? And we'll see if that's true. Okay, it's about twice as far as Jupiter. That's order of magnitude, but they're very close to a 2-to-1 resonance. Right? Okay. Orbital eccentricity, orbital obliquity. Notice that this has significant obliquity. What's that?
You describe what a.
Yeah, obliquity is, if this is rotating like this, okay? Obliquity is the angle from north. So let's say I'm orbiting in a plane. If I have an angle that is like 90 from that plane, I would call the obliquity 0. If I'm tilted into the plane of my motion, then I would call that angle 90. If I'm tilted like this, I would say that I am rotating backwards compared to the direction of my rotation or my orbit, and that would be retrograde rotation. So that's the yeah. So that's, and remember, that's the way that we talk about obliquity as a whole. So we talk about all of the planets only with respect to the plane that they are in. So for example, Pluto is up out of the plane, it's inclined. So of course, it wouldn't make sense to include its inclination in that obliquity calculation. It is tilted, but it's tilted with respect to the planet it orbits. There's almost no inclination for most of the other. Okay, the sidereal revolution period takes about 30 years to go around, only about 10 hours to rotate, so a day is pretty close to Jupiter's day. A lot of moons, a lot of rings. We won't get into it in detail. Why is it tilted? Probably has to do with the fact that Jupiter and Saturn did not form the locations that they are. That their interactions with one another caused the late heavy bombardment, caused Earth to be tilted off of its axis, caused Saturn to be tilted off of its axis. Remember that the obliquity of Jupiter is almost to 0. Jupiter basically was hanging out, doing whatever it wanted, just bullying everyone in the solar system, including some of brother Saturn. Neptune and Uranus probably started quite close to both of them, and were kicked out the outer solar system and life would switch places. This is why Uranus is still big planet. Okay, we've been to Saturn a bunch of times. Saturn has been visited 4 times. Most recently by Cassini. Cassini is where you get all the pretty pictures. These ones are fine, but this is before we had the cameras. Cassini is like, you know, modern iPhone. The funny thing, of course, in order for anything to be sent into space, it has to be something called radiation hardened technology. That means that it can't be the newest iPhone 18 because they need to demonstrate that it will perform well in an environment that is heavily imbued with solar radiation. That does not mean like radioactive materials. It means cosmic rays, X-rays, UV rays, right? So if your material is too sensitive and one little X-ray is going to fry the circuit, then they don't fly. So there's always about a 5-year gap between the coolest cameras we have on Earth and the coolest cameras we fly in space. So that's really something fun to think about, because think about all the fucking sick pictures we saw at the thing like Juno. That's with like an iPhone 3. That's the same technology, as opposed to what we're looking at it on, which is like an iPhone 12. Right?
Is Clipper gonna go by Saturn?
No. Europa Clipper is only going to Europa.
I was wondering if they just line and come go out and come back.
That would be close. That would be sick. That'd be like a tour of the solar system. You need them to line up really well. And I believe they're like this right now in the sky. So it would be like like this. So the easiest thing to do with Jupiter is always to use Jupiter to slow yourself down, swing yourself out, then burn, and then come back again. Okay. Jupiter has the lowest density of all of the planets. It has a very low moment of inertia. We noticed that as much as it did. Its visible surface is even more distorted by its rotation than Jupiter, meaning that it bulges out. It has more of an equatorial rotation. Right? And as you learned in one of the more recent homeworks, you know how to calculate a bulge. Right? If you choose the ellipsoid first, and then you subtract off the sphere hiding underneath it. Okay. Many people just calculated the ellipse. Order of magnitude. Okay. This one definitely has a rocky core. And we can tell that based on measurements of the gravity interior. There are moment of inertia calculations that we didn't go into in this class, but that you could theoretically think about. And that is how a series of polynomials. So for example, let's say we start with a sphere and we add bulges. That might be the first order approximation. But now you need to add a set of bulges that go up this way, do the second order approximation, and then a bulge that goes this way. And so you end up with a very lumpy object. But you can devolve all of those into understanding what the exterior shape is. Now just imagine making shells, concentric shells of different masses all the way down in order to understand the gravity distribution. And that's in fact what we'll do in something called radio science. So radio science can mean both radio observatories, it can mean using radio waves to probe the top of the atmosphere. But one of the really cool things they do is by measuring how fast or slow the spacecraft responds, they can tell whether or not the spacecraft is where they thought it would be versus slightly to the left or right. So as we fly by something that's massive, it goes towards it, and it creates either a lag or faster communication than you might expect. And so we can see changes in the flood. Almost a similar composition to Jupiter. I won't have you memorize these except to say that it's like 96% H2 molecular hydrogen. The temperature is about 95 degrees at the cloud tops. Do you remember what the temperature was at Jupiter? Yeah, about 140, 150, sorry. But that's, yeah, right. It's significantly warm, almost 50% warm. And again, here, the expectation is that it should be about 83. So what does that mean? Heating from that. So notice the difference, right? This one is only about 12 degrees Kelvin. Do you remember the difference that was expected for Jupiter? We can look it up, but it's a lot. So there still is heating coming from the interior. It's just less. Okay. Saturn emits 2.5 times as much power as it receives from the sun. Oh, similar to Jupiter. How does that happen? Right? So there is a major abundance difference. There's less helium. Where's the helium? Helium's obviously like twice as much. So this is differentiated like we saw before, and the helium is actually sunk, right? And what happens, which is crazy, is that helium that does make it out precipitates down as helium rain. Okay, this is obviously differentiation as well, but it's a different type of differentiation, right? When you think about differentiation, sometimes we might think of just like large parcels falling down or convective motion, bringing that material up and down. Saturn also has a strong magnetic field. And it does have the cloud belt system that we're going to see and we talked about before. But one of the major differences is there is less ammonia. So here's the ammonia concentration. It's got more methane than Jupiter did. I guess I should put the next picture up. Next one. And you know, the important thing there is a lot of the colors that you'll end up seeing. You have some water vapor, obviously, that's going to be white, but it's the white and the yellow. And those don't contrast as well as the white and the brown. So on the right hand side is the Saturn clouds, the scene, and then this is Jupiter. Similar. It has rings. So I think we did this already, so I don't know if care anymore. They're nicer. They're bigger. They're more recent. Right? When I was in grad school, we weren't sure how old the rings were. Which is pretty impressive. And so over the course of a decade or a decade and a half, you can go from having an outstanding science question to people actually figuring it out based on data. Right? And that's one of the things that's really great about science. You might find yourself thinking, man, how did Uranus get so fucking? Well, in about 10 to 15 years, we'll send another mission to Uranus. So if that's something you're really interested in, start learning about the giant planets now, right? And you want to learn about the interior and why do we give a shit, and then you get to work on a mission that goes to find that shit out. Okay. Speaking of the devil, so this guy is drunk driving in the solar system, tilted his car on the other side of the road, and he's small. He's a small. So why are they smaller than Saturn?
Yes, they're further out in the solar system.
Yeah, but so that's certainly true. Well, why is that true?
Because Saturn is got something more.
Yeah, let's do a quick experiment. Okay. And here's the sun. Here's the disk. Okay. Now we know that like rocks condense at a temperature about 1500 degrees. So there's going to be some distance. You have to start the disk. That's where the first rocks. Okay. And then at some point, you get up here and water ice condenses. And then you get up here and methane ice condenses. But wouldn't you expect most of the material to be out here? What? Okay, sure. So you would expect all the material to be here. So last material here, and then it like ramps up. But then what's the explanation for not getting bigger as you go out? Yeah, that would be the same. I mean, even if they, let's say they all form here. 1, 2, 3, 4. If I believe that adding more ices makes you bigger, and I would expect, you know, small, small, bigger, 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 bigger. How does the inner solar system go? Small, medium, a little bit bigger, small. Oh, what the fuck is happening here? Right? What am I lying to you about?
Half a lie.
What have I misled you about? Well, we do think that they certainly don't form. They have a very short window with which to form. If you don't form the giant planets within 100 million years, you don't get gas giants because the star blows away the remainder of gas, and they're sort of stuck at 10 to 20 mass core in the center. Let's say you start with the same amount of stuff. Okay? And you disperse it equally as a function of distance. Same stuff all the way up. What happens at the very edge? The most area for that same amount of stuff. Yeah, so you have two problems. One, you have less stuff for a huge amount of area. And to your point, that there's literally it takes longer, right? Like this guy is taking 84 years to go around once. So when you collide with stuff, one, you're going slowly. You stick, that's great for keeping yourself, but you don't hit stuff very often. So you have two problems. One, the area is really big. You won't be able to get a lot of stuff. And two, the collision time. We have to do this within 100 years. So Jupiter can do it very quickly. Because it's in that sweet spot of a lot of stuff, moving fast, grabbing gas and going before the 100 years. Like, have you ever seen those game shows? They run through the Costco and they're grabbing everything in the cart. That's what they do. They have a tiny. These fuckers are going so slow. This here, right? They put it in the next one. You get that? Cool. But that's why they're small. Both of them. And they're about the same size as we'll show. The reason we think Uranus and Neptune switch place, in addition to the fact that it's all tilty, is he's actually small. If I drew it like this, but it's actually like this. Expect they were. Okay. Anything else that you want to see here? Oh, rotating. Weirdo. Rotates backwards, tilted. Got a bunch of moons. 10 narrow rings. Funny me. Okay, Neptune. Let's flip between. Yeah. More massive, but smaller. How could that be? More dense. More dense, good. So let's remember that as I add more material to a gas giant, and you can find this in your Astro 1000 textbook. Okay, as you add more material to a gas giant, size increases, and then it decreases. Jupiter's like here. Saturn's like here. Uranus and Neptune are, I don't know if they count, but this is for hydrogen helium mixtures. Okay, moment of inertia. But the same. pretty differentiated. The albedo we didn't really talk about, they're blue, whatever, who cares? Look how much farther this guy is. Takes almost 150 years to go around. You guys know what's happening 150 years ago?
The Civil War.
Yeah. This guy only went around once in a civil war? Oh, boy. Okay. Rotational period, normal. 16 hours. Pretty close. Okay. This one here? 17 hours, slower and backwards. Only times we've ever been to Uranus and Neptune was Voyager 2. I'm reading. Yeah. Redistribute the spacecraft all the time. This is how we did it. You're talking about it for the solar system. You have to hope that everything's lined up. So scientists are like, it's gonna be lined up, bro. Let's do it. And they're just like, oh, they threw everything together and they hooked it into space. So Voyager 1 and 2 are fantastic. They're still going, or I think only maybe Voyager 1 is still going. But anyway, one of them saw all 4 planets, that's Voyager 2, and Voyager 1 saw the first 2 and then 1. Look at how cool that is. Voyager 1 and 2, like a month apart. What? Oh yeah. We don't ask about that. Okay. Nearly the same size, Uranus is larger, Neptune's more massive, Neptune's denser. Oh. There's a comparison. I guess it'd be helpful if I remember what I've done in slides. One thing I want to remember here is that the Uranus and Neptune objects, the mass of the core here, right, is a substantial part of their body. So we tend to think of Neptune and Uranus as gas giants. But here's what really their atmosphere is made of. Only like 3 or maybe 1 times as much mass. That doesn't mean there's a surface. Doesn't mean that when you jump off the spacecraft on Uranus, you're going to fall and land on some beautiful methane country, right? It's still under tremendous amounts of pressure. It's still under tremendous amounts of heat, right? But it's not like all gas all the way down. You know, make this comparison. We could say potentially 0. It could be gas all the way down. Whereas with Saturn, right, where the atmosphere is 6 times larger than the interior. That's the major thing I want you to notice here. So there's also carbon, nitrogen, and hydrogen. So how do those get mixed in to the core of these giant planets? Carbon, nitrogen, oxygen. So these are hydrogenated compounds. So anytime you hear the word ice, we typically mean the word water, but that doesn't make any sense in the planetary context. So if you want to take C, N, or O, you got to add some H's to it, right? Let's take a triangle. The triangle. Right? And once you do that, then you have some free H's to grab other H's, right? Like water loves condensing on water. Once you start condensation of water, they're like emissions, right? And that's true of a lot of these hydrogenated ices. But otherwise, if you have something like CO2, right? CO2 still makes ices, but at a much lower temperature and a lot less frequent. So the abundance of CO2 or CO ices very dramatic. And especially when we look on something like a comet, which is the leftover building blocks, those can be, they're not perfect, they're not pristine, but those can be very good markers of what the original disk looked like. Right? So you had condensation, these things came together, they were the leftover building blocks that you would have made planets with. And then some of them got kicked out to the outer solar system. Right? Like the Oort cloud in the Kuiper Belt. So when we think about what's in the interior of Neptune and Uranus, it's like that. It's like a comet, kind of all packed together, as opposed to what we think about the interior of our planet, which is much more, lead and like rock, like heavy boys, right? And that, leads to the word ice giant being enclosed here, even though there's no part of the body that has ice. There's water ice clouds, potentially, nothing clouds, but it's not like surface ice. Right? Okay. They have strong magnetic fields. What does that say? Awesome, right? They have rings, yeah. Cool. Okay, Uranus, weird up. The ecliptic points in the opposite direction of revolution. So about 800 million years after the solar system, it escaped. And probably was like this, perfectly happy, perfectly fine, kicked onto its side. You see how that motion explains both at the same time. So now it is rotating the wrong direction and backwards, as opposed to this. It's still awesome. But that at least seems something. Right? So, okay. The contrasts are very small. So we were talking about the low contrast between Saturn clouds. It's even worse for Uranus and Neptune because our eyes are not well adjusted to methane, right? So, in order to measure the rotation of a planet, it's fairly straightforward. So on Earth, if I stand outside of the Earth and I have a spacecraft, I just wait until a feature goes by that I really like. So let's say I love the Andes, and I'm watching the planet rotate. Like, oh, there's the Andes again. Oh, that was about 23.789 minutes or hours, right? Boom, that's a day. For an asteroid, we can do the same thing. But asteroids like to tumble. But sometimes they're tumbling, let's say they're tumbling just like this. Right? And you say, oh, well, now I can just wait until I have a lot of light and then less. A lot of light and multiply it by 2. Or if it's tumbling in a weird way, I'll wait until I get exactly the same amount of light again. And that's the day. Right? Because I can be getting strange combinations based on the orientation, and then it comes back to where it started. That's the definition of the day. Right? If you go Uranus or Venus, Uranus or Neptune, right? Because they're not going to give you very interesting line curves. It's basically 30% gets absorbed, and there's not a lot of features to track until you have something that you can see, right? So when Voyager 2 visited, right, we could see those clouds. And we could watch them. Cloud top temperature. Look at that, that's fucking crazy. 59 compared to 60. It's colder. Now that's an average. But that means that there's no internal heat, just like we have here. That's the same, right? Is that surprising? Because I just said there's a magnetic field. Or let me say it. Is that surprising? Because you don't need to have flux through the surface to have a molten material. Obviously. Cool. Okay. There's Uranus in true color on the left. Helpful, right? You see the clouds? Can't see anything, right? Blue, blue, blue. No. Yeah, on the right-hand side, this is all they've done there is to stretch the contrast. And then they put it into different color. So what they do is they just take brightness, right? And so this is the brightest part of the image, it's right here. Okay, and that's how it's changing. And so if you saw, for example, a blue cloud that was more reflective, that would show up here as like a blob. But there's like no cloud in that image or this image on the left that is more bright than the other cloud. You might be asking yourself, well, why is it brighter here and not here?
How the sun is reflected on the planet.
Exactly, right? So if you have a baseball and I illuminate it with the sun, there is a point that's directly pointing to the baseball. This is called the subsolar point, the point that's directly pointed towards the sun. And the brightness always falls off that, right? In fact, we modeled this. Fine. Right? Now you model the temperature, that's where you get the temperature. Okay. Them all. Okay, Neptune, it's further from the sun, it's cold. Yeah. It has an internal heat source. It emits more energy than it receives from the sun. That's weird. This is Neptune. There's a moment of inertia, 0.23. Very starts. 0.225.
And it's further up, so it doesn't get
Well, these are all scales to one another, right? So even though Uranus, Uranus gets basically nothing of its interior. Neptune gets 3.5 times what we would expect it to get from the sun. Now, it's still very little, obviously. I'm not saying that, but I'm just saying it's kind of a difference, right? And here I want you to notice one more thing. Let's hold on to that idea. Okay. Okay. The upper cloud deck actually rotates more slowly than the interior. Now that's okay. When you think about things like differential rotation, we're not thinking about the interior and the exterior. We're thinking about the interior layer with respect to one another. All right. So this is not saying that it wouldn't have any influence. It does have, but this is kind of strange. So the winds are strong, and there is a great dark spot.
the picture.
Yeah. Right, hold on. See if we can pull it up. So we got time. Oops. Hold on. Not do it live. Oh, I won't be able to find it in time. Okay, let's oh boy. Why did I not have this pulled up? We did the moons, right? We did the moons and rings.
Moons are the giant planets? Yeah. Okay, I don't have it here. But let's just finish with, oh, I definitely won't get through this all. Oh. All right, whatever, I don't care. We're gonna do it anyway. I'll post the slides and then you can go through them if you want. This won't be on the last homework. Okay. I'm gonna find you a picture of the great dark spot too. It looks kind of how you would expect, like a dark spot, but you should get to see it. Okay, I'm gonna really briefly talk about comets. And we already talked about asteroids in some, not a lot of detail, probably not as much as Garrett would like. But we also didn't get to talk about formation. So that's sad. But here we go. This thing here that I want to talk about next is fun though. So we have been talking about electromagnetic energy and how it affects atmospheres, but it also affects particles. So I'm going to talk about radiation in the context of light and how it moves small things. So we talked about the energy from a photon before. The energy of a photon goes like this, proportional to the wavelength. Smaller wavelengths need more energy. Okay. But hopefully you learned something in your homework about something like angular momentum and torques, the rates of change of angular momentum. So in this case, we have something like a force is the rate of change of the momentum. As I can always write, F equals ma. That's the famous one. But it's actually not how Newton wrote it. Newton in the Principia said that F was dp dt, where P is m times v dt. And because we don't want to make students cry, we keep mass a constant. So it's m t. Okay. This is the truth. So if I throw this pencil at Dante, what's going to happen?
Bounce off of it.
I was never said that I was going to throw it at your head. I said, what happens if I throw the pencil, the Sharpie at Dante? What happens? You caught it. And what if I throw this cable at you?
Oh,
You probably still catch it, right? And then what happens? Dante goes back. So the thing is Dante did go back when I threw this at him. You just didn't see it. Right? So it's a very, very small amount. And in fact, as I stand in front of this, I'm getting smacked. Gobsmacked. But it's by tiny things. Right? Because the idea of momentum, we're talking about energy here, right? Obviously, light has a lot of energy. Go outside, I get a suntan, I look great for the holidays, right? But I don't get to move. The photon has momentum that is the energy divided by the speed of light. Okay? It's a real momentum. It really pushes on something. And just like when I throw a pencil at someone, if you catch one pencil, no big deal. If I stand outside and I'm getting light that hits me from here, and I'm getting scattering that hits me from here, and scattering that hits me from here, those kind of all cancel out. And probably the wind that's all around me is pushing me more than any piece of light. Right?
so I don't notice it. But in the emptiness of space, where there's nothing pushing you, suddenly all of those pencils start to happen. Right? Okay. So let's have a look at oval. Oval. I'm going to introduce you to a concept about a revolving body. You take something with radius r, and you rotate. You take the body like that, radius r, and let's have it rotate. Okay. Let's say it's at a temperature T. If it's in thermodynamic equilibrium, what does that mean about the radiation? Very good. Okay, so energy in equals energy out. Very good. Okay. So that's a condition that must be true. Okay, because otherwise the temperature would increase, right? So the power in, the stuff that it gets from the star, right, is going to be the luminosity of the star, how far away you are, multiplied by how big your surface space is, right? R squared. Right? Now the thing about this is that unlike that curved surface we were doing before, we're just going to treat it like throwing darts at a dartboard. We're just going to use the surface area like this, and the momentum, okay, is going to be related to the energy just by dividing by c, just by dividing by the we did that before. You know, right? Momentum is the energy just divided by c. And Newton showed, or sorry, Einstein showed that, so we're taking it as true. All right. So if that's the case, then I can take this thing and I just get c other. Cool. Okay. So now all this stuff is hitting me, and I have a force on the side of me that is facing the sun. Okay. But it emits radiation equally in all directions. Light in all directions. So the force in is going to be balanced. This is the force in. It's going to be balanced with the force out. It's got to have the same amount, right? Or sorry, the energy has to have the same amount going out. So let's imagine that this body is rotating. Let's get a picture here. But from the direction of the starlight, which is shown down there at the bottom, the star is moving with some angle. Okay. Body. Mm-hmm. You're going to have a component of the force in the direction of motion and a component of the force tangential. I'm going to break these apart. This first part is called the radiation pressure. And the second one is Poynting-Robertson drag. Okay. So starlight, let's say, is this way. Starlight is this way. Side. There is this piece in the direction of motion, and there's this piece here. Okay. Radiation pressure. Poynting-Robertson drag. The light hitting you at its edge here is going to pull you back into position. I'm skipping through all of that. I'm sorry. It is fun, but you can do it when you're like prepared. Okay. So the first term is radially outwards, just with respect to R. And And the second one, is strikes at theta. That's the. Um. so, um, The Robinson drag term leads to a decrease in the momentum. And therefore, it's angular momentum. So what that means is that light will gradually decrease the radius until the body falls into the star. This is Poynting Robinson drag. Okay. So we didn't get to talk about it here, but you have bodies migrating in the solar system, moving in and out. And let's say you start out here, here's your sun, and you have some dust rain in here. It's going to retard your motion. That means to pull it back in the original direction, sap you from it. And as it does that, slowly spiral in. Now, this is in competition with other forces, so don't get ahead of ourselves here. We're going to break down each one. Okay. We can talk about the albedo, and there are all these terms that we can add in about how effectively you scatter at different parts of light. I want to show you this competition between Poynting Robinson drag and radiation pressure. Okay. So Poynting Robinson drag takes a long time. Radiation pressure blows away small things. What I just said? Radiation pressure pushes you, Poynting Robinson drag decays your orbit. They are basically in competition with one another, despite the fact that they appear like this in the force factor. Okay? That's because we're in space and everything's perfect. Right? Okay. So they're in competition with one another. And Poynting Robinson drag can take what sounds like a long time to make a body fall into the sun, but it's small compared to 4.5 billion years, right? So you did this calculation before, and I hope you saw in your homework that you can then calculate the decay of an object by looking at the change in angular momentum as a function of time. Right? So you can do that here with this body. It's a lot of math, but I promise you it's really fun. Okay, and you get something like the Poynting Robinson drag. Okay, so depending on where you are, if you're closer or farther, depending on beta, which is one of these scattering efficiency, basically it's a constant. But let's say you're at 180. If you're just undergoing Poynting Robinson drag, how long does it take you to fall into the sun? One. 1,600 years. Oh shit, what? Right? So there's obviously some competition going on. But this is also why small things may not be around us. Right? This is why the intersolar system is cleared out. Not only because we grab our nearby neighbors by definition of the planet, but also because the sun is doing that clearing. We talked about blowing away the gas, but we also can move the dust in a very short amount of time. Right? Okay. So related to radiation pressure, that's pushing out, Poynting Robinson drag, that's pulling in. You have solar wind. And these are particles, ions and electrons, right? It has the same geometry as radiation, it's going out radially. Sometimes there's a little bit of curvature to it, depending on the sun's magnetic field, but for the most part, it acts as a radiation pressure, right? It has an azimuthal component. Okay. So we talked about the fact that light hitting your body is going to slow you down. There's another one called corpuscular drag. So this is the solar wind. What you think, okay, that would push you out, just like the light pushes you out. Well, it actually makes your orbit decay. Okay. But it's smaller than Poynting Robinson, except maybe on molecules and like the very smallest. Okay, finally, let's get to this point here about this rotation. Okay, you have this object, and you get to have the very coolest word that we have in science, the Yarkovsky effect, which says that as something rotates and is illuminated, this changes the evolution of the body. So what do I mean by that? Let's say, you have this perfect circle, boring. Yarkovsky effect, not that important. But if you have something that has maybe different, like one part's redder, one part's bluer, maybe one part's lighter, one part's darker, then as it rotates, it will begin to absorb and emit light differently. Right? So for slow rotators and bodies with quote unquote seasons, right? So for example, we have a season where we point toward the sun and then we point the northern hemisphere towards the sun. The northern hemisphere and the southern hemisphere have different albedos. Right? The southern hemisphere is all water. Most it's much darker than the northern hemisphere, which starts off at the beginning of the year mostly frozen, mostly white, high albedo, and changes its albedo over the course of the season. Okay. So if you have an object like this, with little patches of different albedos, this is much more important. And the recoil of the body from the light emission from either higher, hotter points or cooler parts is larger, right? In order to stay in thermodynamic equilibrium. So if you have some body and it's got some piece that's really good at absorbing light, very dark, as it moves to the night side, now it's radiating all of that into space like a little jet engine, and it's pushing it in a certain direction. Okay? And so this is really cool. So there's a net force in the opposite direction of the sites with the highest emission. This is like, in my opinion, one of the coolest little things because you have these little asteroids and they're all these different shapes and different colors and different sizes. But if you have something that gets really warm, when that warm part points to the night, now it has a little solar power, solar generated like engine. Okay. And this is super important for making sure that we don't get hit by asteroids. Because if they're oblong shaped or they're small and they're weird, then they get a little jet come towards us. We don't want that, right? Okay. Okay. Running out of time, but that's okay. The things that I wanted to point out here, and I'm not happy to go into more detail if you're interested. The first part is that light is like a particle. Right? We know that from quantum mechanics, we know that from optics, but it really carries momentum and it changes orbits. And so you have two different types of drag. You have corpuscular drag and you have Poynter-Robinson drag. These particles, 7-meter sized objects, they spiral into the sun. Smallest dust particles, less than a micron, they also spiral into the sun. But radiation pressure on stuff that's about a micron or smaller, well, larger than, or smaller than a centimeter, these are actually blown out. So you have a population that's flowing outwards. You have small stuff that's being dragged inwards by the solar wind, corpuscular drag, and then you have sort of the centimeter size stuff that's also being dragged in by the PR drag. Okay. And in general, the Yarkovsky effect really only matters for like comets, not so much because they don't fit in our solar system. But when we begin to think, if you get to a point you're working on planetary formation, and you're thinking about how the disk could have gotten all this stuff together, think about there's basically 4 different groups that are all moving, sometimes in concert with each other, right? These are both moving in the same direction, but not these, right? So if you want to go, you start with little stuff that condense, molecules that condense, and you want to build planets, you need to accrete them. You need to build them, physically get them to stick together. And if you just wait for them to hit each other, you're going to take a long time. So how do you speed that process up? get them to cross. So if this guy over here is spiraling in, and this guy over here is spiraling out, then they're much more likely to hit each other. As opposed to if these two dudes just happen to be right in front of each other. So we see rings, right? Rings, they look stable, they look beautiful, everything's going nice. But if you want to start building up mass density, then you have to get these particles. Okay. So that might have seemed like really out of left field, but that's kind of why. Comments, questions, concerns? You know how comments form, you don't care. Anything else? Okay, I think it's a natural stopping point. I will release a homework. Maybe 7. It'll be due on Friday. Is there reasonable? How many questions?
We're gonna have finals to worry about. We have finals.
Yeah, this would be a final. I mean, I'm not giving you a final. Come on, relax.
I say 1 per home.
So 6.
What's that logic?
No.
I was trying to argue my same thing with 5. He for 6.
Well, this is the 6th homework. So
Is it a 6 homework or is it a final? Which one is it here?
well, it's both and. You know, it exists in the superposition of final and homework. So it won't be cumulative. You know, I think I've seen a lot of your work come back and I've seen some progress being made in that respect. I think it's really important to me that you get what we gave. Right, so if you got feedback and said, build up slide 8 and do this again, just do it again. It'll be much easier for me to see like, okay, this person is very good. And what I would like from you, and I'll maybe write this down in an email so that I'm sorry it's not really well that I can see it. Is that you submit the class homework and then write me a paragraph explaining why you deserve your grade. Okay. Anyone seeing Doris?
She upset.
No. Good. You want anyone from here? Who's yours? Oh, no, I'll say.
Would you release the rest of the slides I'm getting expo?
Oh my goodness. Everyone wants slides on time. They want reference material. Yeah, that's fine. I'll do that.